The recording going? Okay, it's going. Hello, everybody. My name is Trask. I'm from the University of Maryland Biocomputational Engineering program. I'm recording this presentation for ENBC311 data mining course. It's on non-small lung cancer mRNA clinical biomarkers. Non-small lung cancer stats can be called NSCLC. And let's get into it. Okay, why do we care about non-small lung cancer? Well, it's a disease, right? People die, but a lot of people die from this one. Lung cancer is the most frequently diagnosed cancer and the most common cause of cancer death globally. And of lung cancer, 85% of lung cancer deaths is non-small lung cancer. Now, overall mortality from lung cancer remains with a 5-year survival below 15%. And on the right there, you see what's called a Kaplan-Meier estimator or curve or plot. And basically, it plots the survival probability on the left. 1 is like 100%, 4 is 40%, and time variable on the x-axis. It could be months, years, weeks. But in this case, it's months. You can see once you get into 8 months or so, you're down like 40% chance. And this is for advanced cases, like when the tumor gets very big. But this is not the case for like smaller tumors. So, and we can deal with those pretty substantially easier. So, therefore, a lot of people, both in the literature and myself, consider early detection of non-small lung cancer to be important. It's not really done much. That's part of why it's so deadly. We're not detecting it when the tumor is so small. People and doctors aren't noticing it, and then the tumor just grows into a big case, and people suffer. Now, before we even try to draw any conclusions or run any tests, what exactly are we trying to use to make sense of non-small lung cancer? Now, there's 3 sample types out there, like to analyze non-small lung cancer. There's the standard biopsy, where we go into the body and we sort of extract a part of the tumor or the tumor entirely, and then we study it. And that's not intrusive. That's intrusive. Hurts the body somewhat. And it's expensive. But there's a less accurate, but not too less accurate, but a substantially cheaper and less intrusive way is drawing blood, looking at the mRNA and other genetic material in it. And the third method is even less accurate, and is saliva, but that's so less accurate that it's not really used right now. I'm going to be using blood serum for the purposes of this presentation. Now, I'm going to be taking mRNA data from blood samples. What does that mean? I'm going to be trying to measure the expression of the genes associated with mRNAs, because the mRNAs make protein, and then the proteins are expressions, they build things, and that we can measure that as the gene expression. And that gene expression level, that amount, often differs for non-small lung cancer for those mRNA biomarkers. So that we can actually measure the effect of the non-small lung cancer on those gene expressions, so that we can then infer based off that on like an unknown patient whether they have non-small lung cancer for detection, for example, and other applicable tests, which I'll mention down the road. Many people in the literature are using mRNA biomarkers for screening, early screening, to see like references 5 and 16. And they also, some mRNAs don't even code for some gene expressions, but they affect other mRNAs or stuff that do code for genes, make genes. So there's a bit of variation there, but they all do measuring roughly the same thing. Now, we know what we're trying to measure now. How do we actually do that? Well, there's 3 methods that need to be used: RT, qPCR, microarrays, and Kaplan-Meier method, which I'll explain on the next slide. But note that the Kaplan-Meier method makes these Kaplan-Meier curves you see on the right. That's from like the first slide. So you can already see some of the applications. First, I mentioned mRNA biomarkers, but there are a lot of DNA and mRNAs out there that aren't affected by non-small lung cancer. So how do we tell if something's mRNA biomarker or just unrelated mRNA? We take the samples and we put it through microarrays, which you can see on the left. We basically we make the gene profiles of each patient and see if the genes individually have some different expression, different sort of effect or characteristics based off of the presence of non-small lung cancer. After we determine that certain gene or a series of genes have our mRNA biomarkers, our biomarkers for non-small lung cancer, we then want to actually measure the gene expressions to quantify it. That's what we're doing with R2Q-PCR. Now let's break down that acronym. PCR, part of that, stands for polymerase chain reaction. And what it basically does is it takes genetic material and amplifies it. It makes more of it. Copies over and over again. It copies so much that we can actually quantify, count gene expressions on a large scale, not like tiny cellular level, but make it big enough that we can actually count. Reverse transcription is just turning mRNA into complementary DNA to help with this. Just make it easier. Okay. After that, we then have a quantified number to put to each gene expression for mRNAs across a certain number of patients, for example. Then we can employ statistical methods such as the Kaplan-Meier method to make sense of it, to visualize it, to make predictions. And that's what the plots from before was about. Now let's get into more. Let's move on. Oh, okay, there we go. Before I get into the nitty-gritty, know that in the blood, which I'm dealing with, there's a lot of different types of mRNA based off of different biomarkers based off of where you get your gene data from. So like platelets, plasma, so on. I'm dealing with like blood serum, plasma, mRNA biomarkers. Just know that the other biomarkers exist. They're valid. I'm just dealing with mRNA plasma biomarkers. Now, there is a third application besides detection and prognosis, prognosis being like survival time with the Kaplan-Meier curves from before. It is treatment so openness of patients, or like susceptibility. Now, have you heard, I'm assuming you've heard of chemotherapy where the cancer patients go bald, right? Now, those chemotherapy treatments don't always work for people. And doctors and scientists have correlated that somewhat with gene expression, with mRNA biomarkers. And so that's another application. If we can, the idea is if we can measure the mRNA gene expressions in people, then maybe if they have more of an mRNA biomarker, that means they aren't good for a chemotherapy. Then we'll be saving them a lot of time, money, and health, spending it on a treatment that just won't work for them, right? That's a third application. And that's what I'm really trying to, those three applications are really what I'm trying to support with this presentation and data analysis. Okay. I said I'm supporting these applications, but what exactly am I doing to support? First, let's understand what I'm actually working with. I was very lucky to be provided with a 99,868 gene expressions for 130 patients. You can see a little example in Excel on there. And know that these gene expressions have been z-scored. That means they've been centered around a mean. It makes it easier to work with, that's all. Now, I have a bunch of gene expressions. I have the same problem as before, which with the that the microarray solved. I have these bunch of gene expressions. Not sure what they are, which ones are the actual biomarkers, right? What did I do to solve this? I selected 54 non-small biomarkers from the literature. I read up through the literature and saw what people were seeing. Oh, this max biomarker does so and so. Okay, I'm going to look at that one. This MUC1, that this other paper says that's a biomarker. I'm going to look at that one, and so on. And so I selected that from the genes and isolate them from the original data and threw out the rest of the stuff that I don't care about. Now, the slide I just skipped through just basically explains that I'm using the computer language Python. You can use either Google Colab or Jupyter Notebook. I use both for this project. And I used some very common libraries I noted. Okay, but what am I using from the libraries? What's the actual like statistical mathematical things am I doing to the data to shape it into what I want? I use what's called principal component analysis, PCA, and I use a specific variation of it called singular value decomposition. What this does is it reduces the dimension of the data down into like easier dimensions to work with, and it gives it various outputs, but the output I'm interested in is these vectors you can see on the right, based off of variation, and it's like there's 130 vectors, one for each patient, by 130 patients as well. There's 130 vectors, and each one for each patient, so 130 by 130 matrix. I'm only selecting the first 5 vectors for the purposes of my data analysis. Not to really burn my computer too much. And these vectors are in the direction of the data of most variants. It's just trying to fit on the data the best. And you can see, look, it's a little scatter plot of data that if you fit on, it's not the actual data I'm using, just an example. Now, once I do that, I have this new 5 by 130 matrix. I then take that and compare it to the data I selected before I fed it into the PCA. So the 5 by 130 matrix with the 54 by 130 matrix. So 130 patients by 54, and the other matrix I just got from the PCA. I put them into two statistical tests. First, the Wilcoxon signed rank test that gives me a t statistic and a p-value. And I also fed into another statistical test called the Pearson correlation test that gives me correlation value, correlation coefficient value, how similar things are. And note that the PCA took individual values of the gene expressions and compared to everything else. So I'm basically comparing each data with each data point of the PCA vectors with the original data. And I keep doing that for every single point, every single gene expression. I do this, and I get two outputs each for each statistical test, as I explained before. But note that each output has five different values for each PCA vector. Okay. This PCA vector thing, there's different values for each PCA vector. I want to compare the PCA vectors to see if there's it's all right to use this data, if there's everything's working all right. That's why I tested out with this pair plot here, to comparing the t statistic values for PCA vector 1 for the Wilcoxon signed rank test, and the PCA vector 2 of the same test. I see a strong positive correlation between those. So that means the data did not change that much across PCA vectors, and that's a good sign. That means the process, the statistical test, and the PCA is working for this one. And I used and I did the pair plots for every single output. And you see, for example, on the left, PCA vector 1, for the t-test, t-statistic of the Wilcoxon signed rank test, across all the other PCA vectors, and just repeat it. We see a strong positive correlation like before, good, but the Pearson correlation, not so much. It looks like a scatter plot almost. That means no relationship. That's not so good. That's a problem. And we'll see more on the raw data down the road. Wilcoxon t-test, the correlation coefficient, the p-values, it holds true. Now, why do I think this error happened? I think what went well for the Wilcoxon test was it was measuring the significance of the gene expressions. That's its purpose. It was determining whether a gene expression was significant when compared to the rest of the data. But the Pearson correlation coefficients, Pearson correlation test was comparing whether individual values were significant when compared to the rest of the data. So whether the Wilcoxon test was measuring the gene expressions, which has 5 PCA vectors, so it doesn't matter which PCA vector you choose. The Pearson correlation test was comparing individual PCA vector values as well as the other 2 variables. So when the Wilcoxon test only had to deal with the gene expression and the patient variables, the Pearson correlation test had to deal with the patients, the gene expressions, and the PCA vectors as variables. So that's why I messed up. Now, here's the raw data plotted. You see on the bottom the T statistic from the rank test from before, Wilcoxon rank test, as the T statistic values the same across the PCA vectors, all the same. Okay, it's working. But see on the top, the Pearson correlation coefficient values, they vary a lot across PCA vectors. That's why there's a problem. Still valuable data though, but the test needs work. We see that across the p-values as well. Okay. Now, why do I say the Pearson correlation test is still valuable despite it not working as intended? The important point is that the Pearson correlation values, coefficient values, indicate both the magnitude and type of relationship. So that's why I still see value in there, even though it didn't work. And if it worked properly, we would be able to measure the similarity and relative strength of the gene expressions when compared to the rest of the gene expressions. So if, say, if a gene expression has a unrealistic Pearson correlation coefficient of 1, then we'd know, oh, it has a positive correlation because it's a positive number, and it's very strong because it's 1. And it goes from, and not 0, like the correlation, the coefficient value goes from 0 to 1. So if I can work on it more, I can get better results in further articles. But what did work, as mentioned before, was the Wilcoxon test. It measured successfully the significance of the mRNA biomarkers when compared individually when compared to the rest of biomarkers, mRNA biomarkers. So significant ones here are ones that are particularly strong, that are the best biomarkers out there. And I did that by saying, using a 95% confidence interval, or in other words, p-value less than 0.05. And from that, I get 27 significant mRNA biomarkers. Excuse me for some water. Thank you. Okay. Now, I selected the significant mRNA biomarkers, and I think these, from my hypothesis from before, these can be used as predictive tests. Now, I want to run a trial test of that. See, okay, can this work? Do these biomarkers make something good? Make a good test. So I developed a Cox proportional hazard model from these mRNA biomarkers. Then I can make a Kaplan-Meier curve from before. But you might be thinking, on the x-axis of the Kaplan-Meier curve, there was time, right? And your gene expression data doesn't have time. And that's true. That's why I'm even luckier to have information about the survival status, whether somebody's alive or dead, and time to last appointment between time to last appointment. At the time between the last appointment and the event happening, somebody being alive or dead when the data was recorded, and the characteristics of the individual patients, same patient, whether they're male, female, smoking status, age. And now I have these two things, these two data sets. Okay, I have the raw materials, but I need to process the materials so I can feed into the machine, the computer machine model. But if I tell the computer smoking status current, the computer will say, what is current? Who is current? I don't understand current. So I do some little encoding with hot encoder to quantify current or gender. Say male would be 0 and female would be 1, and then gender would be the variable. That's basically how the encoding works. And I do that for each of the characteristics of the second data set. And I combine this data set with the gene expression data of the 27 biomarkers from the original data set. And I have have a new third data set of those data. I feed into the Cox proportional hazard model. And then after fitting the model, I then estimate a Kaplan-Meier curve, which is what you see here. As you can see, it does rather well at the beginning, and but it drops off after, like, say 1200 here into like straight lines. That's because I have very few data points over in this later area. The data is just very sparse over here, so we're running into extrapolation problems. So really, I would say my model is this particular model is good for like 0 to 1200 timeline, time after, between time to last appointment. So that's why I restricted that the x-axis here on the left. But the Kaplan-Meier curve is not the only thing good for survivability, and survivability is on the left, like before. I also was able to predict the median lifetimes of patients. I mean, predict as in guess with feasibility. And you can see same time axis for all patients varies. Now you might see like 0 numbers here for some of the patients. That doesn't mean people are dropping dead as soon as we record them on the data, right? It just means that the values are so small that the computer basically says it's small, 0. It's small relative to everything else. So that's like a small limitation of this graph, but it's not too big a limitation, I think. And on the left here, I have the partial hazard of each patient. Now, what you need to understand the Cox proportional hazard model is that there is 2 parts to it. There's the baseline hazard, the hazard independent of all the covariants, all the variables as discussing before, like sex, the gene expression, and so on. And the partial hazard, which is the hazard or like the risk of dying for all of the covariants. And that's what I plot over here. Okay. Now, what can we take away from my little data analysis here? Well, we conclude that 27 non-small lung cancer biomarkers from the literature are significant through the Wilcox assigned rank test. And we should examine these for clinical potential. And we've tested it through the cost proportional hazard model. Now, at the bottom there, you see a note that the presentation has a report with all the references and sources, and also includes how good the model is. But basically, if you want more details, more proof, more everything, it's in there. You have to just take my word for it. There's a report. There's a written article if you want it. Okay, what else? What other outputs I have? I have the Pearson correlation test. It had errors, as we discussed before, but it still has promise, and we just need to work on it more. And now at the end, I want people to. I think these findings deserve attention, not attention, but like further work. Because as you know, the Pearson correlation test needs more work, but also the cost proportional hazard modeling and actually worked as a survivability predictive test to some degree. So if we can work on that, we can get more tests, maybe detection, maybe treatment openness of patients. And maybe we can expand the data set, have more patients, reduce error, and look at more biomarkers to find even better biomarkers out there, so we can select for the very best for tests. So this really is ripe for work. More needs to be done. Valuable stuff has been found. Let's continue working. Thank you for listening to me, and have a good day.